Bonjour, il est 17 heures.
So, hello, it is 5 o'clock. So we're going to make a gradual start. So today, you have signed up for the seminar about large wood in rivers. So for following the seminar, I would like to invite you to click on the right channel. So if you're French, you need to click on FR. If you're English, you need to click on EN. So at the bottom of your screen, you should have that possibility to choose the channel. Can I also invite you to ask your questions using the chat feature. If you have any difficulties, for example, you can also use the chat feature. So while the conference is going on, can I ask you to switch off your microphones and your cameras? So today with us, we have 3 guest speakers, Robert Gubernick from USDA Forest, Margriet Schoor for Rijkswaterstaat, and Michael Moore, who works for Terraform. I'm going to hand over to my colleague now for introducing our partners. So first of all, I will hand the floor to H2O Lyon. So H2O Lyon, can I ask you to speak? Yes, hello Antoine, hello everybody. So we're very happy to be with you today and to co-organize this international webinar. So just a few words about H2O Lyon. It's a university school focusing on research. So it's a graduate school in the French sense of the term. It was started 4 years ago, and we work on water sciences and hydro systems. And we're bringing together a large community of 12 different higher education institutes, over 13 research laboratories, so 250 researchers in all, and 80 students who are doing a PhD. And so we work on 4 main values: interdisciplinarity, the development of international collaboration, links with social and economic partners, and also transfers between research and training. So the aim, of course, is to provide answers and solutions for some of the major challenges gravitating around the question of water. So we organize quite a number of events, and we also support other events like the one that is taking place today. Just a few words now. We've included a new master's this year, Integrated Watershed Sciences. If you want to know more about that, then please have a look at our website. Otherwise, enjoy the webinar. Over to you again, Antoine. I'm going to hand over now to Lisa from the World Fish Foundation. Lisa, are you with us? Can you speak, Lisa? Normally, you should be able to speak if you just click on your microphone.
So yeah, I would also like to welcome everyone. We are very happy at the World Fish Migration Foundation to support this event. We were founded in 2014, and we are promoting free-flowing rivers for fish. And yeah, basically these nature-based solutions are very interesting to us because they really provide a lot of interesting new habitats for fish. You probably know us. Every 2 years, we organize World Fish Migration Day, which raises awareness of migratory fish species all around the globe. So yeah, that's us. I also wish you a very pleasant webinar. And yeah, I hope that you get inspired and install some large wood in your river.
Très bien, merci Nisa.
Great, thank you, Nisa. I don't know whether we have a representative for UCRR. the European Association for Rivers. I don't know whether we have anybody from that organization with us yet. I have the impression that they haven't arrived yet. Not to worry, they will be able to introduce themselves a little bit later on. So this is just to underline that they have supported this approach and by providing information. So straight away, we're now going to hand over to the next speaker. But before that, let me just go through some rules. I will be moderating with the help of Joe Wheaton, who is also with us. Let us just get the slides up. There they are. So if you want to interact with the speakers, can I ask you to write your questions using the chat feature? So, and with Joe, we will pass on your questions to the speakers. So there will be 20 minutes, first of all, with Bob Gubernick, who will be introducing himself straight away. And then we'll have 10 minutes for questions, then another 20 minutes for a presentation. And then with Michael, and then another 20 minutes for Margriet. And then at the end, we will have time to for questions and answers. If you have any further questions that you haven't been able to ask during the 10-minute sessions after each 20-minute presentation. So we have 300 people who have signed up. I don't know whether they've all actually joined, but we've got people from all over the world, as you can see. So that's really quite impressive. People are interested in large wood. So I'm going to stop sharing my screen so that Bob can share his screen. Bob, can you take over now and introduce yourself?
Yes. Anton, do I have 20 minutes or 40 minutes?
Tu as 2 fois 20 minutes.
You have 2 times 20 minutes, Bob. 2 times 20 minutes, okay?
Okay. Where is, this is going to be window. I want to see this one. Open. Let me know, Anton, when you can see this.
For the moment, we can't see it, Bob, says the interpreter.
Okay.
But
let's try this again here.
Coming, maybe. No, it hasn't worked yet. It hasn't worked yet, Bob.
Yep.
Pour l'instant, on ne voit rien, Bob.
So we still can't see it, but maybe it's on its way now. If we just wait a few moments, it might appear. It says that Bob Gubernick has started to share his screen.
Is it running now? Can I get going?
Pas encore, mais ça vient.
Not yet, but it's coming. It's telling us that the screen share has started, but we can't see your screen yet. Ah, there we are. We've got it. Thanks, Bob.
Okay.
Bob, over to you.
Okay. So, hi, everybody. I'm Bob Gubernick. I'm an engineering geologist out of the USDA Forest Service in the United States. I work for the Stream and Aquatic Ecology Center out of Fort Collins, Colorado. I've been working in the restoration and aquatic organism passage field for almost 40 years now. And I'm going to talk to you a little bit about large wood structures and applications. I will go over a number of different things. I have photos given to me by some of the colleagues here that I am showing on this screen. So today I'm going to be talking a little bit about large wood history, large wood in streams, how it gets there, how it goes away, a little bit about design function and what you have to do for design, some anchoring methods, and then go into different large wood structure types and their purchases. So without further ado, this is a graphic by Janine Castro and Colin Thorne, and it shows essentially the interaction between the geology, which overrides pretty much everything in channel form, the hydrology, which delivers the work on the geology, and the biologic component that takes the benefit from these two things. And what you see here in the graphic is that, you know, depending upon where you're at, if you have high flows or low flows, and on the left you have stream power, which is just a function of discharge and width, and then the erosional resistance, which is a function of the geology. And so the hydrology and the geology move the materials around depending upon channel gradient, and different biotic fish, benthic organisms and all can take advantage of some of these different things. Some of them, the biological species, will enjoy lower gradients, deeper pools, things like that. When you get to higher gradient channels, less so. Again, so this just shows, like I said, the interaction between the geology, the hydrology, and the biology. What we do know is that many years ago, in Europe, it's going to be probably thousands of years ago. In the United States, it's about 150 years or so ago. We started removing wood in our rivers in a major way. And we did that to open up the rivers to navigation. And by doing so, we forever changed what these rivers look like and also how they responded. In the United States, we had railroads going up narrow channels. They moved channels over to the side. They simplified them. They splashed dam. And again, all of these changed the qualities of the river and how they look. So here we see a large wood reference condition in a pristine section of river in Alaska. And I really like this image here. And with the wood, it gives a lot of structure to the stream and performs many different geomorphic benefits. So in the image here, you could see the wood that forms the banks. You can see all the old trees that have fallen in the channel that are now essentially become nurse logs for the trees growing on top. They form the banks, they form cover habitat, they sort gravels in stream, they provide deep pool habitat. And the sorting of the gravels has an effect on the spawning, especially for salmon and other things, because they key in on some of these different sediment size types. And as you can see in the photo, the wood is everywhere. It's within the channel. You can see a root fan in the lower right-hand corner that's been embedded in the channel. You can see the logs sticking out that are buried in the banks. All of these are helping form the river shape, attenuate floods, and provide complex habitat for all the different aquatic organisms in the stream itself. So in the natural stream, as in other managed and in managed systems also, wood goes away and it needs to be replaced. So this slide here shows the rate of wood going away from a study in Southeast Alaska by Mike Murphy and Kay Koski in the late 1980s. And what you're seeing here, the B and the C refer to channel types of the Roskin methodology. So the B channel types are higher gradient, steeper channels greater than 3–4%. The C channels are the floodplain type channels that are under 3% typically. And what we see on the graph itself, we have the depletion rate as percentage of the total wood loss per year. And then on the bottom, you see the large wood diameter class. So you can see the larger pieces get lost at a slower rate than the smaller diameter pieces. And what this means essentially is that wood is continually going out of the system. And the way the system maintains its wood balance is you have episodic events that come in and add that wood. When you have a logging action that has removed the riparian forest, essentially you are removing the source of wood that the stream will get over time. And I really like this graphic here. On the Y ordinate, you have the old growth level as far as percentage of wood loading. On the bottom, you have years after clear cut. So you can see that before they logged, the stream was at 100%. And this is the wood that's already in the system. As time goes on, you are losing a percentage of every year. Now, when you cut the riparian zone, conversely, you have wood that has to grow. And for the trees to get to the size that it's going to benefit the stream, you can see it takes a long time. It doesn't really start contributing that large wood till almost 80 years into the action. And so once you do this type of managed cut, the wood that is of the size that the river typically needs takes a very long time to regrow to be able to contribute. So we're looking at 100 to 150 year cycle for this to occur. And I'll just show you the effects on that. This is in Alaska. This is a complex river channel in the Harris River. And this is a photo from 1961, right after the riparian zone was harvested in this area. And you can see all the wood in the channel, the complexity that you see, lots of different islands, wood in there forming different types of structures. So over time, another 50 years later, all that wood is now gone that you see in the channel, and it's become a very simplified single thread. And this is essentially the thing that we're trying to avoid. The aquatic habitat requires that channel complexity, because within that channel complexity, different organisms are keying on that to increase their species in the stream itself. So in order to create that complex habitat that forms the deep pools, that forms the cover habitat, that sorts the gravel, you need to have wood throughout the entire history of that stream. So in some cases, it means we have to go back in there and intervene. So one of the ways that nature intervenes is it has an event that puts large wood in the channel. So that can be a mass wasting event, such as a debris flow or a landslide. You have wind throw and the blowdown that gets into it. You have flooding that erodes banks and makes trees fall in. You have just the normal lateral migration process that rivers go through that eat in underneath the trees, and the trees fall in and start to contribute. So again, it's not that they're getting trees all the time. A lot of this is episodic based on flood, fire, essentially large precipitation events to get in there, but there's also smaller wood that's contributed either by blowdown, wood decay, etc., throughout the time of the stream. So I'm going to move into design a little bit. So in design, we have a couple of publications that I recommend that folks get a copy of. These are all free, that have been put out by the Bureau of Reclamation, the Corps of Engineers, and also the Forest Service. They're very good. The one on the left, the National Large Wood Manual, goes through everything from concept through implementation and all of the required things you need to consider when designing a large wood project. The one on the right is a publication the Forest Service did to help you with your computations of buoyancy and drag based on that. There are other calculators out there. Again, in order to be successful, you can't just do feel-good work and put wood in streams. It has to be designed, it has to be implemented properly. So let's go on, look at some of the forces that are acting on the wood. So in this image here, you see a free body diagram. And in that free body diagram, it shows all the forces acting on it. So you have buoyant forces, you have the force due to gravity, the force due to flow, the drag force on there, frictional forces, uplift forces. And again, all those need to be considered in your structure, and each of the different structures are affected by some of these different forces. So in a stream, in the natural system, when the tree lengths are greater than the bank full width, typically those wood pieces, the structures that they form, are in the stream long term. They're very stable. If they move, they typically don't go far. When you have tree lengths that are much less than bank full, that's typically the case that you have in larger rivers, and their position is temporal in nature. They don't stay there long. However, you can work in these larger systems. You just need to do design, and they need to be ballasted properly to stay in place. Wood can be used in all of these locations, and you can make it stable as long as you understand the forces that are acting upon them. So I'm going to talk about three main forces, basically, or three situations that you have to account for that do the most work on the structure. So the first one is buoyancy. And we know that buoyancy is the flotation of the wood in the water. The wood weighs less than the amount of water it displaces, so it floats. So in order to keep the wood in place, you need to ballast it. And that ballast is done by a number of different methods, weight, entanglement, etc. If you don't, once the wood gets a certain amount of water goes up on it, it will get up and float away. And that's the last thing that you want to have happen if you're just doing a demonstration project. You want your wood to stay in place and you want it to work. So you have to ballast it against buoyant force. So here's just the analysis. Again, simple. The density of wood times the volume of wood minus the density of water times the volume of water times the acceleration of gravity. And that is your buoyant force. And typically, we like to have a factor of safety of 1.5 when we're dealing with a buoyant force. Another force for those structures that stick out from the bank or that will capture a lot of material is drag force. And the thing with drag force is that you need to remember, one, that the stream bank position changes in time. There's lateral migration, there's local erosion around there. So when you're doing your drag force analysis, you need to do it for the worst case scenario, how much further out you think the structure will stick, how much more cross-sectional area that it will take. So, and the drag force, again, that's all of you have felt this when you've walked out in the stream and you feel that force of the water pushing against you. Again, that's a function of the water velocity, the area that you're blocking that the water is going, and then the drag coefficient. And again, depending upon the structure that you're building and what you're building out of, there's different drag force coefficients. Next one that you need to be concerned of is scour. Scour is very important because if you get too much scour underneath a structure or around a structure, you may have an overturning force that can cause the structure to fall in and rotate. The other thing that scour does is that it can cause your structure to start losing ballast materials. If you have a lot of embedment and you scour up underneath your wood, that wood, the sediment that's ballasting it can fall out underneath, and you could lose enough of your balance so that either drag force or buoyancy could cause your structure to lift and go away. Again, when you're dealing with this, large amounts of rack material, scour abatement logs further underneath your structure are important to have. And again, understanding scour, lots of ways to calculate scour. Pretty much all of them are wrong. What we typically like to utilize is doing multiple methods. We will check it with an empirical equation, but we will also let the stream tell us how much scour it is by the residual pool depth plus a factor that we apply based upon how difficult it is to scour the material. So in a fine grain system, you know, scour can go deep. In a coarse grain system, it's not as deep. Again, understanding that and building and designing for it is important. So here's the drag force analysis. Again, function of velocity, density, acceleration of gravity, and the drag force coefficient. So in order to keep those down, you have to have ballast, some anchoring methodology. There's lots of ways to structures. You can embed them where you will essentially dig a trench and place the log in there and put the material over top, and there's enough material on the top to overcome the buoyancy of the wood and keep the wood in place. You can use piling. Piling are great. You can, the piling, when you're putting piling in a gravel bedded, cobble bedded river, it's a slow process. You have to excavate large holes. That piling that you can see in the middle photo actually has the root fan attached and is essentially about 10 feet below the water line there to help resist the forces on the structure that we're building. If you're in finer grain settlements, fine gravel, sands, cohesive materials, you can drive piling in, as you can see in the upper right-hand photo. If you're in a case where you have shallow bedrock, would somebody turn off their mic, please? The mechanical anchoring you could utilize is driving man array anchors, duck-billed anchors, dead men into the ground. And typically you're using a mechanical anchor in a case where you can't use any embedment with, it's shallow bedrock. So your veneer of gravel is not very thick. Or you don't have any other better methods and you need to have it fixed solidly and not worry about any movement or loss. And that's probably more in urban situations, semi-urban places or immediately above bridge structures, etc. And then the last one is entanglement. Entanglement is great. You don't need any ballasting. Essentially, entanglement is entangling it into other trees, understanding which way that the water is going to push these trees so it locks itself in. It's more amenable to small rivers, small streams, headwater channels, etc. So to get into some of the structures now and talk about the salient aspects of those. So here we find ourselves in the bend of stream, and we're going to construct a meandered bend log jam. And a meandered bend log jam is a complex of wood in the bend that essentially the main purpose is bank protection and stabilization. One of the great features that it causes is cause deep pool habitats. It's very complex as far as structure goes. There's lots of void and cover space for organisms to hide in there. It captures small materials, organic detritus, etc., that benthic organisms need. So it helps feed the food chain. Not only do you have a living structure where you have organisms living within it, but it's also helping feed some of the other structures that's part of the food chain there. Typically, the pools form in these structures from the apex downstream is the deepest portion of the pool. So you need to have good scour protection through there. They can be configured in numerous different ways. Here you see a plan view of a project that I did in Wisconsin here. Essentially, I used whole trees, lattice worked them all together, and then used some of the bank materials when we laid the bank back to fill in some of the void space in there. And in these examples, you can see a number of different configurations. They can be configured in various different sizes and lengths, again, depending upon where you're building it and how you're building it. That one in the lower left, that is all wood ballast because we're right next to a road embankment. So the wood weight that is piled on top of one another is higher than the Q100 and has sufficient ballast in there to keep that structure in place during large floods. Another one is the apex jam. Apex jams are used to form complex multi-threaded channels. They're used to protect islands, and they produce some great hiding cover and some small pool, crescent shaped pool that forms up above. When we're configuring this, typically we are embedding the logs down into the bed, as you can see here, 1.5 meters to 2 meters of depth. To ballast our structure, we have scour logs under the front to help keep that there, and then a rack of material on the face. And again, this is scalable. It can be small for the small streams. It could be huge for larger rivers. Another couple examples. When I'm typically building these types of apex jams, I have logs that stick out to help capture material coming down the river. So it is a self-sustaining structure. It forms a little bit of an island behind there. I will typically plant vegetation, willows, etc. in there. As you can see in the lower left-hand photo, this is an existing island that we're building onto with additional materials to keep that side channel multi-threaded nature intact. A lateral bar jam is a log jam that's placed along the margins, and the main intent for a lateral log jam is to narrow up the channel. We'll build these off on the side. They'll be high and wide. In the photo on the lower left-hand corner, you can see the mound of gravel that's behind there. These are bank building structures. If you have enough of them, essentially they function like a groin. So they provide a dead zone of an eddy behind the structure, and it mounds material in time. Typically when we're building that, the material that we excavate out of there to place the wood in and bury it is mounted up behind there. But as the structure works, again, there's a low, no velocity zone behind them, and materials in suspension and materials being kicked up during larger storms, bagful events, and greater mound up material on the backside of these. And again, slowly but surely, passively through time, narrow the channel back up again to proper width. And just an example from Pennsylvania for some recent ones that I built. And again, the size is scalable. In a low energy wetland type situation here where we're trying to narrow the channel, we're using the wood in here. You don't need to have a huge amount of ballasting the wood. There's not enough velocity, and with the piling and the weight of these things, it's really tough to move them. Plus, water doesn't get that deep across the wetland floodplain here. It's very large. Just some other examples from Washington, Alaska, Pennsylvania. This large one up over here in Alaska, you can see it's fairly substantial and goes into the woods to build a larger shadow structure to help accumulate material behind there to help narrow down the structure itself. Wood can also be used to provide protection for critical infrastructure. I've been using large wood upstream of bridges to help gather wood during storms to keep them from plugging the orifice of the bridge or the culvert downstream. I also use them to protect highways and other residential infrastructure. So the upper right-hand corner is a large, essentially landslide type style deposit that you would see along the margins of a area where a landslide went through. This is essentially a really large mound of logs that are woven together, and they're protecting a state highway behind that got blown out during a flood. Again, the structure is designed so that the wood ballast is higher than the Q100 flood, and it's all woven together so that when the water starts pushing on it, it locks wood together, pushing it against one another even more, and is more difficult to remove. In the bottom one, built a meander bend jam with an island associated with it right behind there because it's very low-lying floodplain to protect several buildings that you can see behind the structure here. This is a panorama view, so it looks like the bend is going the opposite direction, but it's just a function of the panorama view of the photo. And this is essentially to stop the river from running right into the houses in back, because that's what it did during the tropical storm Irene that happened before I built all these structures. A deflector jam. A deflector jam is a redirective structure. So you have log jams. What we basically talked about is you have log jams that are made to take the water and make it work locally. You also have log jams, and like this, the deflector jam, where the logs are orientated to redirect flow back towards the center of the channel. The deflectors also are used to capture more wood. In this design, I have deflectors low and on the bed, and those are for utilization by aquatic organisms and to maintain a pool during lower water conditions. Then if you look up, there are other logs that stick up higher out of the stream, and those are to capture more wood and redirect flow away from the bank during higher storms, because we know that water flows perpendicular to the orientation of the wood at flood flow. And as with structures, when you have the wood that sticks out, it captures and it makes these structures last longer. Wood structures, again, depending upon how fast they rot, the size of the material that they have, how much water they're in, whether they're above water most of the time or below time, can have various shelf lives of age. I use larger pieces of wood because I want to have the efficacy of it lasting longer. And again, depending upon where you're at in your decay regime, if you're in really humid, warm weather, your wood is going to go away faster and rot faster than if you're in colder climates. And when we build these things, we want them to last as long as possible. So again, think about size of the wood and the species of the wood. You want to try to use the least decaying type wood, most rot resistant wood as possible. The thing that you have to watch out for about redirective structures, especially the deflector jam, is if you have a lot of recreational boat traffic, kayakers, canoeists, rafts coming down the river, you want to avoid this type of structure because it becomes a public safety issue. The other ones, meander bend jams, a lot of those other ones, there's not wood that sticks out very far into the channel, and they're much safer for streams with a lot of recreational boating recreation on it. Here's just some examples again. One up in Missouri. You can see the high logs up above, and you can see the lower log in the water just causing a riffle down there. On these ones on the west branch of the White River, they're low-lying deflector jams, and you can see the large pools that form associated with them. Cross-channel log jams, cross-valley log jams are really good structures when you have a incised channel that you're trying to bring up again. Essentially, you are providing enough wood roughness that the stream drops its bed load and begins to grade behind. When you work with these kind of structures, you can't just think about the channel itself. You need to work across the floodplain more because you're going to be increasing the depth of the sediment in the channel. That's the intent of this. And when you do that, again, you're going to be reactivating floodplain, and you want to make sure that you're not causing a potential avulsion. So we work these structures going from valley wall to valley wall in many of these cases. They are not necessarily always essentially a log dam type structure. They are porous. In time, they can plug up and backfill. Most of the time, they fill up with sediment. They capture some sticks. There's places on there that are still porous, but it's accumulating material up above because it really slows velocity and changes the hydraulic gradient of the water surface, and essentially it drops its load back there. So here we see some old wood in the channel, essentially forming a cross-channel jam. You have one that the water flows over, most of the time, the one down in the bed, and you can see another log that's up above that's suspended on the bank. We do the same thing when we build these. Here's another image of wood going across the channel, many pieces being placed in a reach with a downstream cross-channel jam. And you could see, here's what it looks like at a normal flow on the left-hand side, and on the right-hand side, it's a bankful flow. And you can see a lot of the wood is still out of the water, especially all that you can see up on the floodplain itself. The wood is embedded in the channel, or entangled in the trees, or of large enough mass, it's not going to move. As we move smaller down, you could use bits and pieces of trees and root wads with stems attached to them to form towwood structures. I like towwood structures. They're amenable to small stream. Essentially what they are is it's a bunch of wood, logs, root fans, all chunked up and placed down to scour depth into the bank. And then you build a core fabric soil wrap bank on top of that. And that is vegetated. And there's lots of void space underneath these types of structures. Like I said, they work real well. The key to them is getting that vegetation established. If you don't get the vegetation established on your soil wrap core fabric blankets, then your structure is going to go away in time. This whole structure, like I said, it relies on that vegetation colonization, whereas with a lot of the other log jam type structures, it doesn't. I built a large river variant of towwood. You know, towwood again was meant for smaller streams. I use it on very large rivers, and essentially what I make is a large wood raft, and I build the bank up on top of that. And these logs are sized so that they go back. I understand that I'm going to get some scour, but they're embedded deep enough that they never fall in. There is a set of scour logs placed probably about a third of the way back from the face, and the logs are placed over top of that. And then you use logs and root fans and small logs to chink in. You'll put fabric down. You'll put your soil material down with fascines, and you'll build that repetitively going up. And you can see what it looks like in the lower right-hand corner. Those logs that stick out are ice fenders. And here's a picture of what it looks like once it's completed and after years of construction. Then you could do beaver dam analogies. Joe Wheaton's pioneered this. It works very well in historic areas where there's been beaver in there that have been extirpated from trapping and historic management. And it's a structure that's small, hand done, used to back up water and retain more water on top of the wetlands. We use it a lot in the West. And then you could build small hand structures. And those hand structures, again, are placed with human beings. They're typically entangled and not embedded. And you have to do them where you have trees and could get them. So it's a very opportunistic style. It's very cheap in nature. Hand crews can make this. We typically build these with grip hoists, block and tackle, and entangled in the trees. Again, they work really well. Again, but they do require some design. You need to know how big of a tree you need to overcome ballast. You need to site them in places that you can entangle them so they're not going to get washed downstream, because a lot of times they're just strictly cut logs. And then the other thing The other thing is placing wood on the floodplain. Don't just work in the channel, utilize it all the way across the floodplain. And with that, you can use fascines also, again, small bundles of sticks and twigs. So with that, I will entertain any questions.
Eh bien, est-ce qu'il y a des questions?
Do we have questions to Bob? You can ask questions on the chat if you want to. And, you know, as indicated at the start. So if you have questions, yeah. Do you have questions? You can chat your questions in French or in English. In the meantime, Bob, I do have a question for you. It seems to me that you talked about a guide from the ice first, which talks about all those techniques, which describes all the techniques. There's a guide apparently which is available. Can you tell us more about it? Well, could you give us the reference? We'll put, if you send us the reference, we'll put them in the website for the seminar.
Certainly. The guide that you're talking about here is the National Large Wood Manual that was produced, and I'll quickly share my screen again. And that National Large Wood Manual was produced by the Bureau of Reclamation and the Army Corps of Engineers. And it is the complete manual for large wood restoration. It goes over concept, the importance of large wood, how to design large wood, all the different salient features that you need to consider, harvesting, access, placement, types of equipment, etc. in there. It's essentially the one-stop shopping that you want to have if you are going to practice this. It's a very large publication, but again, it's very well put together with everything you always wanted to know about large wood restoration, but was afraid to ask.
Donc, je vais commencer par la première question en français.
I will start with the first question. You use a lot of logs with the root wad. Can we use logs without the root block? The next question is in English. I will leave it to. So first, the first one. Do you always have to use the root wad as well, or can you use simple logs?
It depends upon the scale. The wood with root fans, the reason why they're so good is that if you look at a weight distribution in a log, that root fan, the first 5 or so feet of root fan and stem is as heavy as the next 30 to 40 plus feet. So, and then also the root fan has a claw. So if it breaks away, it doesn't go very far. You can use logs. They just make things a little more difficult. If you're using small structures that you saw on the hand, those are mostly all logs themselves and can be used. Typically, when I'm building these types of structures, I'm using 30 to 50% of trees with root fans attached. Some people are concerned about taking the roots out, but we shake all the dirt out. We put the slash and other things from tops that we may not use or branches that are cut off back on there and scattered, and we have found no deleterious effects so far.
So there was a comment and then a question. There's a comment from Dean Morrison, said, fascinating, Bob. Here in southeast of the UK, we're mostly working on smaller structures and headwaters, primarily to mitigate peak flows for flood prevention. But then Graham had a question. Would you be able to point him to information on decay rates or considerations for working in tropical environments?
You know, one of there's a couple of publications that I use, and they also cover it in the National Large Wood Manual. there's not a huge amount of information that I've been able to find for tropical type woods as far as decay rates. Most of the decay studies I've seen are for North American tree species. I have not done a huge amount of looking for tropical environment woods, but I would strongly emphasize that anybody building these structures try to utilize the most rot resistant tree type as possible. Also, if you are in very warm, humid areas with high decay rates, to use as large a tree as you can, because if you use too small a one, it will be gone in a short period of time.
Great. There's, let's see, another question from Bill about if you have any examples of designed wood jams that have created stage 0 or forced multi-threaded, maybe stage 8 type situations.
The stage 0 is a little bit different than large wood restoration, even though large wood restoration is a portion of stage 0 construction. Typically what I'm doing in here is building log jams to cause multi-threaded. I can provide a couple of photos. Some of the photos that I showed for the apex jams were turning a single threaded channel into a multiple threaded channel by dividing flow.
Antoine, maybe back to you.
J'ai une autre question pendant ce temps-là.
I have another question. We see the structures you have in rivers. How can will not last? So how can we make them last in time? How can we avoid the degradation of material? What species of trees should we use? You know, for example, pine trees are suitable, and what are the diameters as well? And to conclude with these questions in French, well, there is always a problem with outrooting the root one, you know, because it's always a problem with stability of the bank. So they can. What is the choice of species for a longer durability of the structures?
So in North America, cedar trees are the most rot resistant trees, and then you start going down. So I like building with multiple different types of trees. So I use both conifers and deciduous trees. Again, I'm not familiar with your tree species, but there are within the different types of trees. So for instance, conifers. So Doug fir, cedar in conifers lasts a long time compared to yellow pine in the South. So those with a lot of pitch, trees with a lot of pitch in them, tend to last longer than those that don't. With deciduous trees, again, if you have, for instance, cottonwoods are they rot very fast. They go away even in a large diameter tree. So typically when I am using trees, because I never know what exact species that I'm going to wind up getting, is I base a lot of decay, one, on the structural needs of the trees, but also tend to go towards larger pieces as my key pieces. So a lot of times I'm calling for my trees with my root fans to be at least 18 inches in diameter. Then my face logs, other things can be smaller. You just need more of those to make up and do the same thing. So again, I will provide Anton a couple of publications that he could post that I have for North America, and then you guys can look to see if there's been some research on your side of the pond.
Looks like we've got a couple others here. There's a question about how well these structures you're showing us can hold up in high magnitude flood events. Flash floods here in the south of France, triggering huge discharges, typically 5 to 15 cumecs. Do you have those sorts of high discharges in rivers in the US? Can they withstand those sorts of things?
Yes, I actually have a whole presentation on a project that I did in Missouri, where my structures went under 35 feet of water. So that's like 13 meters of water. And it was a Q500 event, 150,000 cubic feet per second. It pushed off the highway bridge that was over 30 feet in the air. But of the 4 structures that I had built downstream, 3 of them survived the large flood. 1 of them was lost in the flood. And they also accumulated a large amount of other wood on top of them. So you can keep it. You just need, again, proper ballasting. Your anchorage needs to be there based upon the forces that are on the tree. And your structure needs to be configured properly. So there's both important salient points of design and salient points of construction that have to be paid to, but you can survive very, very large floods.
And Antoine, how are we doing on time here? There's a couple of more questions, and then I could always ask one as well. But
donc il est 18 heures.
It is 6 o'clock. So we will take 3 more questions, and then we'll keep the other questions for the end. So there's 2 in English, 1 in French. Thank you for that presentation. So there are challenges for 2 banks, and we don't want the plots to be modified. We don't want any loss of surface. These methods with wood, can they be applied, or should we always think about the movements of the bed, erosion of the bed with that kind of event?
Your stream bed is, if I'm understanding.
Si j'ai bien compris.
The trees, when they're ballasted properly, the bed will move just the way the bed always has. What the trees do is they sort the gravel and help create various types of channel form, pools, islands, things like that. So it's not going to stop the sediment from moving downstream. It just changes the sorting that you will see in the stream bed itself.
Peut-être en précision. En fait,
Perhaps just to add to that, I think that the question concerned laterally erosion on the sides, on the banks.
Oh, okay.
Can you sometimes guarantee that the banks are not going to change?
So with wood, there's always some erosion and scour that changes. Erosion is a natural process. Streams move. They're not locked into the place most of the time. And if they are locked into place, typically it's because there's been some type of management on there. So with your structure, when you build it in there, you will, during large storms, you will probably see some erosion in some adjacent bank. It's not going to cause an erosional event that's going to go and translate itself further on downstream. It's doing the same thing, the same erosion that would happen as if a tree fell in to the stream. So if you're putting wood in the stream, you have to understand that erosion is part of the calculus of these structures, because a lot of times the intent of these structures are to provide pools, which means that scour has to happen in the bed. When we're using structures for scour abatement or bank protection, then they're made to prevent that bank erosion at that point, such as in the meander bend that's getting close to some houses or whatever that you're trying to protect, or a very, very large fine grain bank that the stream already has way too many fine grain inputs that you're trying to attenuate there. With these log structures, typically I'm doing planting in and around them. I try to encourage planting trees on top of them because in time wood rots. And what you want to have happen is you want to have the trees growing to take the place of the rotted wood. And when the structure is done, you want to have trees on that bank to replace all the trees that were in the log jam. And that's just the evolution of those structures. As you recall, with the large wood reference condition photo I showed you in Alaska, they had all these trees that you can see coming and sticking out of the bank with all the trees that are on top. Those are the nurse logs. They're rotting, they're providing nutrients to the soil, helping provide structure and attenuating the erosion.
Okay, you actually answered one of the questions, which was about augmenting these structures with living wood and getting, you know, recruitment and growth there. So that's great. There was another question about the cost of these things. Do you have any sorts of rules of thumb, whether it's, you know, per meter or per structure? You know, I know it's quite a variable thing, but
it is. So the things that cost the most are the actual acquisition, harvest, and mobilization of the materials. The materials may need to be hauled from many miles away from where you get it. One thing that you want to avoid doing is cutting down the trees in the vicinity of the banks that you're working on. That's a self-defeating thing. You don't want to cut down your living trees to replace them with dead trees in the bank. Work around them. So what I find my historical costs, which includes harvest, mobilization of the materials, the building of access roads to go do this, the installation of the material, and the planting. Essentially, when I look at it, it's about $1,000 a tree. And that is highly variable. The cost for a tree with a hand crew can be a fraction of that, could cost $100, but still yields a huge amount of benefit to the stream. And again, these things are all scalable. So if you have to haul in trees from very far away, it's going to be much more costly for you than if you're doing it from close by. The actual installation of the structure is, for the most part, the cheapest portion. Typically, I average placing 3 logs per hour with a couple of excavators. So that cost, you know, for a structure is typically less than a day for a significant structure. You know, a significant structure, say 100 feet long, could have 30 to 60 pieces of trees in them. Again, that's a day, 2 days maximum work. So it's a function of how much it's going to cost to get you there, where your tree is coming from, and the time that it takes to put the wood and gain your access. Sorry, I can't be more specific.
Merci beaucoup, Bob. Donc, on a
Thank you very much, Bob. So the introduction did delay us, But Margriet, would you like to take the floor now and join the co-hosting team? And would you like to share your screen? Maybe you would like to introduce yourself, Margriet, and tell me when you're ready. So if you want to, please share your screen, Margriet.
Yeah, thank you. I try to share my screen now. My name is Margriet Schoor. I'm from the Netherlands, but something is not working now. Okay.
Si, ça fonctionne.
Yeah, you see my screen?
Yes, we can see your screen.
Yeah, okay. My name is Margriet Schoor from the Netherlands, and I will tell you about the experiences of Rijkswaterstaat in applying large wood in a river with navigation, like the Rhine in the Netherlands. Even kijken. A moment, please.
Excuse-moi, Margriet.
Yeah?
Sorry, Margriet.
It's changed?
The presentation has disappeared.
Okay, I try again. You see it now again?
C'est bon?
Yeah.
Oui.
Yes, it's good now. We can see it.
I work as a river ecologist for Rijkswaterstaat.
Je suis écologue pour Rijkswaterstaat.
Now I hear the French myself.
Sorry, that's my fault, the interpreter's fault.
Okay, sorry, I go further on. And Rijkswaterstaat is part of the Ministry of Infrastructure and Water Management in the Netherlands. It's responsible for construction, management and maintenance of the national infrastructure, such as roads and bridges, waterways, shipping, but also water systems. As a water manager, Rijkswaterstaat is responsible for water quantity, water quality and shipping, so all together in one ministry. In addition, sustainability is a focus the last years. Even kijken of het nou goed gaat. Here you can see the content of my presentation. I start with a short introduction of the Dutch Rhine because I saw many people of abroad. The Rhine is the largest river in Western Europe. It's one of the busiest shipping routes in the world, and it connects the harbor of Rotterdam with the industrial Ruhr area in Germany. In Holland, or the Netherlands, there are 3 main Rhine branches in the Rhine Delta. I give you some photos. The Dutch Rhine is a strongly regulated sandbed river with groins, which makes the river smaller and deeper. Most ships sail in the Waal branch, which is the main shipping route. There is a 10-kilometer stretch in the River Waal with a longitudinal training dam, which separates the short channel from the main channel. So in that place, we break down the groins. This is the smallest branch, the IJssel, which is also regulated with groins. And then the last branch is the Nederrijn. 3 years changed the Nederrijn into an impounded river branch. Partly the banks are protected by wooden screens, like you see on the photo. And they are filled up with small willow branches, but they rot very easily. So we had to replace about 1/3 every year. We do have floodplains, embanked floodplains, which are flooded nearly every winter. This is a photo of a summer flood in 2016. And these floods are important for ecology because during floods, there is an exchange of aquatic organisms between the river and the floodplain. The Dutch rivers, as the Rhine, has changed a lot. By the 19th century already, the floodplain consisted mainly of grassland. There were still substantial plots of forest, often planted for land reclamation. You can see this on this old map. The river was regulated and most of the riparian forest disappeared over time. With it, the value of the habitat, this valuable habitat also disappeared. The Netherlands is a densely populated country, and you can imagine the risks of flooding are high. Therefore, flood protection is of great concern. And as trees in the floodplain rise to flood levels, they are now actively removed from the floodplain area. So there's little riparian forest left. For 30 years already, the Netherlands has been restoring the Rhine. This gained momentum with the Water Framework Directive in 2000. More waters in the floodplain were reconnected with the river. The transition from water to land was made more gradual, so there's now always shallow water. And large wood is added to increase the habitat variety. On the map, you can see the projects where we reintroduced large wood. There are currently now 18 trees anchored on the banks of the Dutch Rhine. Nearly 100 more trees has been installed in the side channels and the backwaters. Up till now, we used mainly oak on the banks of the river and oak, willow, and poplar in the side channels. And there are plans in preparation for about 200 more trees. But you keep in mind, this is a very large rivers. So we have about, I think, 150 kilometers of rivers and then 200 trees, maybe not so much, but that should be finished before 2027. A floating tree is considered a safety hazard for shipping in the Netherlands. It mustn't get into the propeller of a ship, and if an accident occurs due to collision of a ship with a tree, it minimizes the chance of successful progress of the reintroduction of wood. Therefore, we ensure proper anchoring of the wood. Otherwise, we wouldn't have gotten permission either. The trees up till now are anchored with steel beams. You can see them on the left. There is an eye welded onto these, to which a chain is attached that secures the tree. The steel beams are vibrated into the riverbank with a crane. Once the trees are secured, they are pushed further underwater. And at normal water levels, you don't see the beams. This is also safer for canoeists and swimmers. The trees, there is a pin through the trunk, and on each side of the trunk, there are two eyelets, and there is a sturdy chain goes through it to attach the tree to the beams. And then each tree is attached in 2 or 3 places to be sure that it stays on its place. Another method we used is with ballast. And we ballast the tree with concrete slabs, 2 of them. And the chains are attached to eyes into these plates. And the required weight of the plates is calculated, just like Bob told, taking into account the buoyancy of the tree. But luckily, when we use a tree in a side channel, the anchorage is less steady. Because if a tree becomes detached from a side channel, the risk of collision with a vessel is reduced. And after all, the wood cannot float out of the channel very easily, and therefore the anchorage is lighter, and that is cheaper. For example, the chains are less heavy. Steel cable is sometimes used. There's sometimes only the cables around the trees and not through it. We use fewer beams, and sometimes wooden beams are used. We are still in a phase of trial and error. We also use concrete slabs in the side channels. And also mechanical anchors, folding anchors are used. I have a picture of them because they're into the bottom of the water. The trees are intended to be underwater. That is where they have the greatest ecological effect, we think. In addition, they rot less quickly there. And in impounded rivers with a fixed water level, that's easy to achieve. But in the Rhine branch and the IJssel, the difference between the average water level and the low water level is often much more than 2 meters. And therefore, we lay the trees at different depth. You can see it on the photo. If the trees are too deep, we think that no light can reach them, and then no algae will grow on them, and then the ecological effect is maybe less. And then the other thing is that side channels can fall dry at low water stages, and then the trees get dry and they rot more often. But we don't know yet, because we are doing this only, I think, 7 years now. We used some constructions, for instance, the protection of a riverbed. Bob told it tow wood. On the photo down, you can see the root ball of the logs. The logs are pushed into the bank. So, and this is in a very curved bend, but there was no erosion, so we think it works. Nothing happens. It's good to try. I think we should do more, because we still use a lot of stones on other places. Another construction, but what we made was a wooden construction to influence the sediment transport. It's placed in a very shallow bend of the river, and 4 wooden screens have been made, and the logs lie between these wooden pillars, and there we used larch, and the pillars are 8 meters long and 6 meters into the riverbed. I try to recognize some success factors of the project, and an important issue is that we an important factor in the placing of large wood in the navigable Rhine is that we take safety very seriously. We work with engineers who advise on nautical safety and flood safety. And for us, that's quite easy, because they're my colleagues. I see them during lunch. I see them. They could be working next to my desk. In consultation with them, we do not place wood in the waterway itself. So always in the banks or in side channels. And the closer to the waterway, the better the anchoring. We also did some calculations on the flood safety, hydraulic calculations, and this sometimes limits the amount of trees per plot we could use. So I'm really a bit jealous on the photos of Bob showed us. A second success factor was the communication during the project. We made a guide for contractors, a film, a flyer, a website, and using dead trees to improve Rhine water quality drew media attention. And what helped also is that third parties, independent ecologists, embraced the project, and they communicate that too. The third thing is that we started small in a river branch with little shipping. And that didn't cause any problems, and people got used to it. And we were able to scale it up into ongoing projects for nature development and project for flood protections. And the last success factor, I think, is that we monitored. We monitored macroinvertebrates, fish, and morphology. And we measured the effect of the wood on aquatic organisms. And in doing so, we feed the communication, and we also improved the implementation. And we always said, when it doesn't work, we will stop. Then I want to show something about the monitoring. What's living on a tree we used. After some months into the water, the woods are covered by filamentous algae. And on this algae, we find diatoms. And the diatoms, that was food for lots of macroinvertebrates. And they were fed by fish. So the whole food chain get a boost. And the boost of the food chain plays a key role in the ecological recovery. It's not only a suitable attachment site for algae, but also for mosses, sponges, and eggs for fish. And fish can hide them on the branches because we use not only logs with roots, but also with branches. And the wood also provides flow variation. Bob told that already. Which in turn gives variation in sediment from gravel. And together it makes the river wood, we call it river wood, a suitable habitat for more different species. And in addition, the wood is also partly above the water, and it provides a landing site for birds and insects. As on the stone in the Rhine, the majority, my computer accu is a bit low, and I talk quicker because I think it's a problem. I thought it was automatically. We have a lot of invasive alien species in the Rhine, and they're also dominating on the woods. But looking into the native species, we found on the wood many target species, characteristic for flowing water. However, these were mainly chironomods, that are non-biting midges, but also some caddisflies like the one on the photo on the left, which was new in the Netherlands. And the species richness on the wood was higher than on the stones, and so was the Shannon-Wiener diversity index. We find that a good result. We also did some fish surveys and saw that the fish uses the river wood as a nursing area, a foraging area, and a shelter area. And near the wood were fewer non-native species such as gobies, and species diversity is higher there. As expected, large wood in side channels affects the morphology of the side channel. At low water level, we could see this very well. And we saw scour pits due to erosion near the trees. But we also saw sand deposits near the trees, and in many places of in these side channels, the rest of the bed consists of silt, so that was more variation. This summer, the Rhine was extremely low, and this also allowed us to see the large wood in the short channels behind the longitudinal dams. These trees are normally very deep and usually hardly any branches stick out above the water. But now we saw gravel sedimentation there in addition to sand. In the short channel, the water flows faster than in the side channels, so that explains the gravel. And we could see that despite being deep, filamentous algae were growing on these trees too. Maybe we should ask ourselves how long it takes until the tree is totally buried under the sediment. And then we could place another tree above it. An important observation was that after 7 years of being underwater and above the water, even the softwood of the willows and the poplars, like on the photo, did not enormously rotten away. All branches thicker than 20 centimeters were still present and sturdy, and smaller branches, however, often disappeared. We say always that the tree itself, it should be at least 40 centimeters. Because we don't want to bring every 5 years a new tree. Of course, there were difficulties too. We want to use trees with branches and root ball, but they are hard to come by. And using large trees and our preference for hardwood, such as oak, also results in high transport costs. And the permit process takes a long time. And we have to consider safety of canoeists and swimmers. Another factor is that in the beginning, we didn't take into account the cost of signage. And we only just have started organizing the inspection and taken into account its costs. And some trees are laying now too high due to the low water level of the Rhine. So monitoring means that we are constantly learning, and that's important. We will now inspect once every 3 years, and we will replace, if necessary, on the riverbanks, then more often than in the side channels. And we try to reduce costs using local willows and poplars, and we want to improve the ecological effect if possible. For example, by placing trees closer together, resulting in more 3D structure and a larger morphological effect. And if possible, deeper placement of the trees, which has two, okay. So, to conclude, even in rivers with navigation is possible and effective to place large wood. It requires more and good anchoring and signaling. Despite the wood being small, relatively small in a large river, there is a local effect on morphology, and together with the wood as substrate, it increases habitat variation and thus species variation. Colonization from upstream has brought in species that previously couldn't find a suitable habitat in the Dutch Rhine. That was my presentation. Thank you for your attention. Any questions? I stopped then sharing if it's possible, and I hope my battery will get on. Stop share.
Ok, merci Margriet. Alors, pendant que les questions éventuellement arrivent, je voudrais...
Thank you, Margriet. I just want to tell you that on the website, well, the visual conference will be broadcast, or replay. There will be about 10 videos concerning projects made with dead wood, and one of the videos was done by the Rijkswaterstaat concerning this the operation for the installment of large woods in navigable rivers, and a French version and an English version as well. So I don't see questions for the time being. I take advantage to inform you that before Mike says it, that we at the We intend to continue with all the webinars on the deeper topics, especially one on PDA, the beaver type dams made, man-made beaver type dams, and possibly one on the passive restoration techniques. So I won't tell you more for the time being, but this is an idea we had and we want to share with you anyway. So now questions now. I will take the first question in French. Is there a specific orientation to be favored for installing trees in the river vis-a-vis the time, you know, the durability and ecological gain?
We might have lost her. Her battery might have died. I don't know. Yeah, I think her battery really did die.
Donc, écoutez, on va enchaîner de suite pour pas prendre trop de retard.
Therefore, well, we won't run too late. 6:35, Mike, please take over and we'll get the question by email to Margriet. Thank you. Mike, are you with us, Michael?
Yeah. Yes, here I am.
Okay, nous y voilà.
Thank you.
Et aussi, donc,
okay, share your screen and
pour la continuation de ces éléments que tu nous transfères.
And talk, and you know, and you can mention the idea you had with Bob about the continuation of this project.
Okay. Okay. Great. Well, listen, thank you, Antoine, Réseau Rivière, and H2O Lyon for all the work that you're doing to help us evolve our river management practices. Thank you to Bob and to Margriet also for your fantastic presentations. My name is Michael Moore. I'm originally from California and I'm now living in the Southern Alps of France. Before moving to France, I was practicing as a design consultant, working on the design and installation of restoration projects in the Pacific Northwest, primarily in Oregon and Washington. And I see that there's a few people out there listening in from out there. And so in that particular part of the world, it's salmon country. And because of heavily declining salmon populations, there's a lot of resources going into improving those populations and restoring natural habitats for that purpose. And so because also of the natural habitat that is the presence of forests and woods in the Pacific Northwest, the practice of installing large wood has been able to develop and be refined and standardized over the past several decades. After a long time, like everywhere else, where we were removing wood, and particularly even the departments of Fish and Wildlife were removing wood because they thought that it would be better for fish. And now there's hundreds of millions of dollars going into putting the wood back in. And so this gives you a sense for the corner of the world that I'm talking about, Oregon and Washington, located between California and Vancouver, BC. And here's a short list of firms that I've worked with or worked for that or represent some sense of authority in the restoration world, really to give you a grasp on the idea that there is a thriving private sector that is specialized in this kind of work. And so I've spent a lot of time with Henderson and Biohabitats, worked with Wolf Water Resources and ESA and Interflu. And all of these groups have extensive experience, not only in restoration, but in particularly the context of restoration using large wood. Oh, it's going the wrong direction there. So as my longtime friend and colleague and mentor, Matt Cruiser, surveys the scene doing what he does best as a lead construction manager for biohabitats and conservation biologist, we will look quickly over on an overview of this talk. I'm going to probably be complementing the previous talks by adding a more anecdotal and conceptual overview, walking through what a project looks like, establishing its objectives and what potential objectives might be, and then how those objectives are converted into design and construction considerations. I will then look at different basic building units that go into these structures, and then look at a couple of project examples of how these units come together. So why put wood in rivers? This is a fantastic graphic from the Freshwater Trust that displays a lot of elements that we've already heard about complexity, about reconnecting the stream to the floodplain, about creating pools and spatial contexts for habitat, about sorting sediments. And all of that comes down to this complexity that has been brought up over and over in the past couple talks. The interaction of hydraulic and morphological complexity. And so I've added some arrows in here to give you a sense for the types of hydraulic complexity that can be developed when we add wood into a system. Down at the bottom, there's little curly arrows that represent the diffusion of energies that can take place when these complex forms are introduced. In uniform channels, oftentimes hydraulic energies are concentrated and can produce unwanted effects regarding erosion. And so this diffusion of energies is an important aspect. Below that, you see arrows that demonstrate the interaction that can be augmented by this practice between the channel and the hyporheic zone. Can be beneficial for water quality and managing decreasing temperatures. And then the larger arrows, the blue arrows, give a sense for the idea that when we increase complexity hydraulically, we're giving much more different diversity of hydraulic regimes into the system, so that there are many different pathways and velocities and turbulent degrees of turbulence that are introduced, allowing different species to benefit. And so as a result of this diversity and complexity, we're improving ecological niching and species mobility. So you have detritus and organic matter that can be grabbing onto these structures and feeding these niches with nutrients. And then because of the hydraulic complexities that are added to the system, different species at different life stages can find the preferential paths that they need in order to move around in the system. Now, in terms of the context of salmon or of any fish that is moving upstream in a uniform channel, they don't really have places to rest in between movements. And so you know, a fish that is downstream could move into a side channel, and from that side channel move into a pool or behind a structure, and giving that mobility much more possibility. And so here's an example that I found nearby where I live here in the Gironde River, a tree that fell in and is demonstrating within its first year in the stream a lot of these dynamics. So first of all, you can see that there's a pool that was created around the root wad. There's high flow refuge. So when there are high flows, fish can hide behind the root wad there and have the ability to not have to struggle so much under those conditions. You can see that gravel has been sorted downstream of the root wad as well, beautifully, and that you can note upstream and around that area that there is no sorting, so that representing the idea that the system doesn't have the representation of different grain sizes available. And then again, flow, diffusion, and redirection. You have flow that's going to move around the root wad, pushed off up into the floodplain. And in fact, you can't see in this photo, but just on the other side of the tree, there is a side channel that's forming. Of course, the roots themselves are diffusing energies that might be concentrated during flood flows. And then there's another piece of wood in the foreground that is across the flow there that is also redirecting flow. This one being a log without roots. And as Bob had mentioned, the flow will move perpendicularly across the length of a log. And so these are the types of things that we want to be thinking about when we're designing with intention. So bringing all these concepts in to a particular site and understanding what the objectives might be, or what might be possible in a project. We want to be thinking about this flow. What does flow look like? How can we modify flow through redirection, through dissipation, and through flood storage potentially? We want to be looking at whether water quality is an issue, how we want sediment to be impacted, whether increasing sediment by directing flow into embankments or stabilizing embankments to reduce sediment for water quality purposes. And then again, mentioning the sorting of sediments as a possibility. Looking at existing biota, what species are native or invasive and who's preying on who, and how we can avoid predation of target species. Looking at the habitat needs of those different species, and then a point that Margriet had spoken to that often is overlooked in these projects is the opportunity for education and acculturation of this practice. In a lot of places in the world, wood and rivers is not a good thing by public opinion. And so when people see wood and rivers, they ask questions, and that provides opportunities to communicate how river systems work, how complexity benefits those systems, and to help people get connected with the systems that they live in. And so from these potential objectives, we move toward design considerations. So I'll go through a list of potential design considerations. First of all, looking at infrastructure. Our site selection will be directly related with what structures are downstream or along the lateral portions of the sites that we're looking to restore. The presence and the dimensions of those structures, who's managing them, and what tools they have available to them for that kind of management. We'll be looking at flow regimes, of course, as with any project in the waterways. We want to be looking at the forces that are imparted by the flow as they act on the structures we install, as well as on the sediment associated with the project reach. And then, commonly we look at the 2-year flow as well as the 100-year flow to understand those forces, as well as the water surface elevations that we can expect. In terms of habitat development, of course, we want to be considering which species we're targeting and where those species can benefit the most within the system. One consideration that's important is whether in-channel habitat or off-channel habitat will most benefit the species that we're targeting. There are studies that have shown that salmon specifically, but many species who have access to the floodplain are much larger ultimately in their development and in different life stages, and therefore much more resilient in ultimately at some point further on reproducing. We want to be looking at existing wood and trees in the system. Bob had mentioned entanglement, so can we use existing trees to stabilize the structures we want to install? Do we want to be planting so that forests that may not already be present, that the riparian zone can be continuing to supply wood over the long term to be replacing the wood that we've installed? And then can we be expecting wood to move downstream that will be able to be recruited by the structures that we're installing. And then flow redirection. Do we want to be directing flow into embankments to increase the presence of certain sediments, or away from embankments that are that need protection? Are there side channels or off-channel habitat that can be activated by using logs in a certain orientation to move water in places that we want it? And then anchoring and ballasting. I know this is something that we all really want to get our head around. What kind of stability can we expect from these structures, and what methods can we use to have some confidence, and that our project owners and that the stakeholders can have some confidence in the stability of this work. So looking at buoyancy, looking at the geology, understanding if bedrock is going to be a limitation in the vertical direction in terms of implanting piles. Are we going to be using boulders exclusively for ballast, or is there a requirement for hardware? And then what sizing will we need to be using? And then project evolution, right? Looking at these projects as with an intention of initiating natural processes that are otherwise missing from the system, and that those processes exist over long periods of time. So what will this project look like next year, in 5 years, in 10 years, in 50 years, not 100 years from now? What impact will wood decay have? Will there be more contributions from the live wood that's existing in the system? And what happens if there's a 100-year flood the next year? Are there failure modes that we can plan for so that our structures will stay in place for as long as possible? And then this separate slide really to put an emphasis on the idea that within the design process, we want to be thinking about the construction process as well. Now there are a number of factors in constructing these that are important for any project in a waterway. But for these projects, because we're often working in sensitive environments where access is difficult, we immediately want to be in the first steps thinking about how are the machines and the transport vehicles going to be accessing the site? How will we be moving materials from this place to that? How will the excavator be sitting on the embankment when it's digging in a root wad, for example? Each structure will need to have that level of consideration. Each piece of wood and each element of the structure will have to have this. How are we going to get this done piece within the constraints of the sensitive environments that we're working in? So moving on real quickly to the basic materials units, and I'll kind of move through this quickly so that we can get down to the project examples. We have 4 basic elements that I'd like to introduce here. First of all, root wads that we've talked about. These are logs with the root fans attached, and then logs without the root wads attached. There are pin piles and brush. And so what you have is a diversity of scale here, where logs can be anywhere from 30 to 60 centimeters in diameter and anywhere from 5 to 7 meters long. A pin pile is going to be more maybe in the 25 to 30 centimeters in diameter and maybe 3 to 5 meters long, so that it can be easily manipulated and driven into the ground. And then brush is all the fine sticks and slash, what we call the material that's generated by producing these units. We take that with us and we stuff that in under these structures to provide that smaller scale complexity that I was talking about earlier. And so real quickly, looking at some pictures of root wads and pin piles, just to give you a sense for how these are used, what they look like, some of the different ways that they can be implemented, the scales. Here, looking at, you can see a couple of examples, both in urban and more natural environments where tow wood is being used, root wads are being used with their high complexity to diffuse concentrated hydraulic energies. And then pin piles, also being driven here with a special attachment to the excavator. And so how do these elements come together? I wanted to talk about two project examples, zooming in a little more closely to the mouth of the Columbia River on the border between the states of Oregon to the south and Washington to the north. This first project is a habitat restoration project on Rock Creek. Rock Creek is a tributary to the Clackamas River, which then contributes to the Willamette River, and then ultimately into the Columbia River and out into the ocean. The Clackamas River Basin Council was the owner of this project and was hoping to improve habitat quality and upward stream mobility of salmon species in this reach. So here's an overview of the project reach. The light blue color gives you a sense for where the 100-year flow water surface elevation would reach out to in the floodplain. And then the darker blue is the 2-year flow, what we call ordinary high water in Oregon and Washington. You can see that the darker wood symbols are the wood that will be introduced for the project. And you can see that there's wood in the thalweg of the river, there's wood in the embankments, there's a little tributary, the Trillium Creek on the bottom right, that's coming in that we wanted to load up with wood. And in this case, oh yeah, and then further down at the confluence of the Clackamas River, there's wood in the embankment that is more focused on stabilization. So we have a lot of habitat creation here and different structures with different purposes. And then you can also see in the floodplain, within the 100-year floodplain, there are elements of wood that are just individual pieces of wood scattered here and there, with the expectation that those elements will see water less commonly and with less force. And so will be less mobile in high flows. So a couple of structure examples that went into this project. This one is a lateral bar jam that is intended to create a pool and at the same time in specific locations to stabilize the embankment in this location. The location and intention of this structure is associated with the fact that the embankment can be excavated. There aren't any obstructions to that excavation like native trees that we want to preserve. And so oftentimes it's where an embankment is already oversteepened and we have the opportunity to dig it out in order to stabilize wood with the sediments in place. The second one here is in contrast in a location where we do want to be preserving existing trees. And in that case, we're using the trees as a stability element in combination with thin piles on either side. We are stabilizing using the pin piles and the trees. And then a couple details to note here, using anchor pins, in this case, driving rebar through the logs to provide stability at their cross connections. And then one other detail to note here is that these projects often specify that the logs in the upper left corner, the note says that all exposed ends of logs shall be broken and not cut. And that is with the intent of mimicking the natural conditions. And so I just want to show you some before and after photos. First, in the middle section of the reach on the left, you can see the before condition, relatively uniform channel. There are no pools. It's basically just one long riffle. And then on the right side, immediately after the project was complete, you can see how different, there isn't as much water in the channel at this time because it is immediately after, but how different the result is. Here is a picture on the bottom right, several years later, and you can see how the system has evolved. Wood has been recruited and there has been a bit of movement in the system. And so also wanted to show you some pictures down at the confluence. Here on the left, again, the pre-project condition, and then on the right, the confluence with the Clackamas River with the presence of the wood after installation. The structure on the left there is one of the structures that we saw that is where the trunks are buried in and the root wads pointing out to receive high flows from the Clackamas River and to diffuse them. Okay, now moving on to the second project, now on the left bank of the Willamette River in Fano Creek. This is in a highly suburban area in Tualatin, west of Portland. The project owner, Tualatin Hills Parks and Recreation District, wanted to protect a trail that runs through a park along Fano Creek. And you can see how erosion is threatening the stability of that trail. And so they requested that we come up with a solution that would include wood. So from a technical view, you can see there are two meander bends threatening the trail. And this particular type of structure depends heavily on the embedment of piling, of pin piles into the embankment. And you can see on the right, there's a boulder toe at the base to ensure the stability of the toe of the structure. And then at the top of the structure, an encapsulated soil lift that Bob had talked about earlier. So we'll see some pictures of that. So here's the project just after completion. A couple points to note. You can see that the wood has been installed so that as much of the wood is exposed to the surface of the structure as possible. And then there is rock that is filled in behind. On the right, you can see a log down in the stream, and this log is intended specifically to redirect flow so that the flow has more of a tendency to take that bend as it's moving into the zone. Also, you can see just under the soil lift that's over the top of the structure, there are willow cuttings that have been laid in beneath. And there will be an entire planting campaign that goes in over this, as Bob mentioned, because it's critical to make sure that the vegetation that is planted takes hold before this really takes on a heavy flow. And so here's some pictures. That next season, once the storms had a chance to come in and move through the system, you can see that sediments have been deposited, showing evidence that there has been a reduction in velocities and more stability. So that's what I have for you today. Thank you very much for your attention, and I'd be happy to take any questions.
Merci beaucoup, Mike.
Thank you very much, Mike. So we'll just wait for people to ask questions using the chat function. So concerning these projects, I can talk about France, not Europe. So being able to add these visual elements, developing this, seeing what the possibilities are. I'm sorry, there is interference. Mr. Reder has his microphone on. Please, can you switch your microphone off because we can hear you? Please switch your microphone off. It's still, thank you. Have you compared these technique in a standardized way between a balanced water way and water which doesn't have enough sediment? What about the pebbles in the bed? Do they move? And what about incision? Is there any incision?
Mm-hmm. Okay, yeah, well, these are all definitely questions that are site specific. You know, we want to be looking at what the sediment dynamics are in the system for all of these projects for a number of reasons. when it comes to the stability of our structures, we want to understand whether the native material that we're using to bury those structures or embed them in will stay there and how long. So, you know, for example, when we install a root wad with its stem into the embankment, we put a couple of large boulders on that. And when we do our force balance analysis, we don't take the burden of the soil over the top into account, because we want to plan for the removal of that, potential removal of that burden of soil due to erosion. So again, taking into consideration failure modes, we want to make sure that the ballast that we put in place is sufficient so that any changing conditions that might occur around the structure will not compromise its stability. So we're looking at sediment movement from that perspective. And then we're also looking at the influence that the wood has in the system. So we will be targeting sediment management and the movement of water toward that sediment management with these installations. So redirecting wood, as I mentioned, toward an embankment in a stream where maybe it is sediment starved. And then otherwise, and what is often the case in the Pacific Northwest, where we're trying to reduce erosion for stabilization purposes, protecting infrastructure, but also because fine sediments are effectively a pollutant. And so reducing the input of fine sediments is something that we're targeting often with these projects. So your question is really pertinent, and it's something that we want to be looking at with every project based on what's present in the stream, what kind of hydraulic dynamics we can expect after installation, and in terms of ensuring the stability of the structures.
Juste pour compléter ton propos.
So just to add to that, can I just remind you that there are cases where these structures are implemented. This is what Bob was saying, in order to fight against erosion and incision. And of course, you've got to look at sediment that comes from upstream. You can have beaver log jams or other techniques. So there are different things that can be used to deal with this kind of problem. I can't see any other questions for the moment. Joe, would you like to say something?
Well, yeah, I have a question maybe that I'd be curious with how all three of the presenters might answer it. Thank you to all three of you for excellent presentations. I think a bunch of the questions and a bunch of the emphasis in the sort of design guidance and some of the case study examples is on stability of wood, and stability of woody debris structures is absolutely an important design criterion or goal in certain contexts, like you were just highlighting, you know, if there's some critical infrastructure or navigation, you know, issues, et cetera, But, you know, I would argue, at least if we're kind of trying to get towards natural conditions, you know, stable wood jams and wood not moving is not necessarily the, you know, a sign of a healthy mobile wood and structures that are more ephemeral. And I know that makes things less predictable, but in some settings, who cares? You're out in the middle of a place where there aren't impacts. And so I guess my question to all three of you is, can you kind of comment on what are those sorts of situations where we can allow a little more space and a little more flexibility and maybe focus on my structure that I built lasting isn't necessarily the dominant design criteria?
I could talk a little bit about that, Joe. Where I can, I let wood do what it does. I'm not as concerned, especially if I have like very long reaches downstream, where my trees are, you know, as close to bankful as possible. Let them do what they want to do. The problem that we run into is that, especially in the situation that Europe is in and that the eastern half of the US is in, is that they're in the beginning stages of utilizing large wood restoration. They have been in a culture of wood removal for hundreds of years. And it is tough to change the mind because everybody is in a fearful base. And part of the fearful base is just how folks have treated wood and the lack of understanding. Like I see a lot of people after floods going and cutting up full length logs, cutting the roof fans off, cutting the logs off, and they're causing themselves more problems because of the mobility of those logs or canoes in the stream. And the thing that you want to go slowly with, because I've worked from West Coast to East Coast with the wave of large wood restoration, and if you're doing demonstrations, if you're in your very beginning, you want to show people that you can keep wood in place. As once it is not a demo anymore for you, then you could start bringing them. It's an incremental educational thing. I think that we just have to overcome. And also the other thing is managing expectations. People think that when you build something and it moves or rearranges, that it's a failure. The educational aspect has to be brought in, that when you're dealing with wood, wood moves in systems. It's not a failure. It collects at other points. The thing that's a failure is when you first do your structure and you haven't educated everybody, and then all of a sudden people come back after the first rainstorm and either you've lost the entire structure or parts of it. And that's where managing expectations and the educational aspect comes in.
That's great, Bob. I'm curious, Michael, if you have anything to add to that. I mean, Bob, another way of thinking about that is on the managing expectations. If you're setting up the goal, focusing on a noun, a structure, a pile of sticks, a piece of wood, versus the goal being the process, for example, of wood accumulating, then those are different. But people don't necessarily always hear what you're trying to say. And I hear you on baby steps on the expectation management. Michael, I'm sure you've seen a lot of this too. Yeah, indeed.
Yeah. Couple elements I'd like to mention. Well, the project on Rock Creek that I showed, there was a 100-year flood the next year that came in. Next year, it wasn't even the next year. It was, the project was in the summer, and then in the winter we had a 100-year flood. And you know, the client, the Clackamas River Basin Council, is well aware of the importance of process and the intention of stimulating and regenerating the processes of the stream. But when they saw the impact of that flood, they were shocked. So as prepared as we could be for the impacts, you know, we had structures, for example, one particular structure that was embedded in the stream and was halfway excavated out by the flood. It was still there. You could see the rebar pins, you know, that we couldn't see before, and it wasn't quite as beautiful. But I was loving it. I showed up on site, and I was my partner and I, who designed and installed the project, were just giddy. And you know, the client, of course, is thinking about, well, that log that's over there now, that cost me $1,000, you know, and so how many logs are we losing? And they're not necessarily thinking about how many logs were recruited from upstream. And so, you know, expectations are critical, certainly. And you know, I know Bob and I agree on this, that I would avoid using any hardware in any project wherever possible. But sometimes there are measures that are taken just for reassurance, you know, so that if there is failure, like I said, thinking about what failure modes might occur, what does it look like when this structure floats downstream? That's one of the reasons, for example, why we've moved away from cabling. Steel cabling was used a lot in previous times. And we've seen now that when a structure that's cabled together moves downstream, it's a scary thing and can really become a big problem. And so the use of rebar is an alternative where if a structure ever does end up coming loose, that it has the ability to fall apart and the individual members can act as they move downstream. I think another point that's worth considering in this is that when there's a flood, the movement of wood is oftentimes the least concern of people who are managing rivers. So they're concerned about the damage that's being done to infrastructure, primarily to people's homes, to bridges, to sewer lines, to railways. And the wood that's going to show up in log jams after a flood, the majority of that wood is wood that's present in the system, whether or not your restoration project took place. And so, you know, if the conditions are sufficient for an engineered structure to move or to quote unquote fail, then we're designing for it to be the case that if that happens, that you know, the flood that had made that happen is going to be doing a lot of other damage in the system that will take emphasis over the fact that the logs that let loose from your project ended up lodging somewhere else.
Alors, peut-être justement, juste pour rebondir là-dessus, je voulais faire un...
Okay, just to react on this, to do a return experience on the torrential rivers in the south of France. Well, it was shown that when there is a heavy floods, it's not the dead trees or the windrow, but there is so much a lot of healthy trees ended up being in the river. You know, the system is not just by you know, by the trees that fell off the banks because of the power of the flood. Despite all the artificial structures, there will be a wood transport. This was measured, you know, and in that respect, this is why sometimes it is better to provide well, like the way to deal with a river, you know, we have to, you know, some trees, you know, will float anyway, and anyway, they will have to be removed from the bridge as well. Well, there was one last question, last question from Michel Bramard. It says, have you been able to test on the same river those different techniques by comparing the simple or the entangled and double session, and so the constraints should be more deposit or less pulling out or less loosening. So could you have a quick answer for that? Have you been able to test your systems on one river?
Yes, we have many different techniques and structure types on the same river system, and all are functioning well. The one thing I will say is that entanglement is a method of ballasting more for medium-sized and smaller-sized channels. In large rivers, because of the force, the flood height, it isn't always the best technique to use for a ballasting method.
Merci, Bob. Merci, Bob. Alors,
thank you, Bob. Well, we have to close now the meeting. Well, thank you all for your participation, the speakers, the participants. But before we want to place in the chat a score between 1 and 5 to express your satisfaction. 1, disappointed, wasn't. 5 is great, you know, amazing. So it will be for us a sort of a scoring survey. And in the meantime, let me tell you that the video that will be put on the YouTube channel, all documents will be in a Drive document to collect all your indications with all the documents. And we hope that we'll continue. We do this again with the various partners, H2O, and the interpreters who spent quite a lot of time who learned the system. We thank you to the translators, ladies and gentlemen. Thank you very much, sir. Thank you, Antoine. So made it possible for you to understand the technology. And thank you to the partner host, the CR, World Fish Migration. Thanks to them, we've been able to reach more than our network and to have participants in the English language. Anyway, so thank you to all of you. Very warm, Bob, Michael, Michelle. Maybe a quick word before we close down, and I will let Joe conclude. Bob.
Well, thank you everybody for the invite and sitting and listening. If you have any questions, Antoine is going to put up my email. You can email me. And the thing that we would like to know is if there is enough interest in a technical training. This would be a design class. If you could please let us know. If there is, we can potentially plan on one in the future here. Thanks again.
Yeah, great. Thank you so much for your attention and your interest. It's really exciting to see this practice grow and evolve. And you know, I talk with people a lot about it in France, and the interest has really evolved over the past few years from, yeah, I've heard of that and it sounds interesting, to we want to do that. We just need to know how. So, you know, this is the start of that. And, you know, I think there's a lot of potential for further educational opportunities. So don't hesitate to contact myself or Bob. My email address is mike@terraform.com. That will also be available. And with any questions or interests, it's the kind of stuff that we're passionate about. So we're excited to share and to continue to develop our understanding together. Thanks.
Great. And with those inspiring talks, we now have some ideas for addressing this chronic structural starvation of wood from the diets of so many of these rivers, and ways to start feeding it back one meal at a time and getting it back as a healthy part of these systems. So thank you to H2O Lyon and all of you for your participation and wonderful questions. And we look forward to seeing you at the next one.
Thanks so much, everybody. Really appreciate your support.
Eh ben, je laisse H2O faire le nécessaire pour l'enregistrement. Merci pour votre soutien.
Super.
Nice, okay. Thank you very much for this great webinar, very successful. Congratulations to all speakers. Have a good day or what's left of it. Okay, bye-bye, guys.